see something familiar, oh, I can see and if, but it actually doesn't mean anything. You can make a C program look like sort of like a Visual Basic program. Probably a bad idea to do that. So I'll give you a very simple example here. This is 3 equals THREE equals 3, which means from here on. Now this is the other thing about the assembler. You don't have to define a label before you refer to it. In other words, you can refer to a label all you want, and then define the label at the very end. It will still resolve it just fine. Okay, so not like C where you have to define everything before you use it. This one allows you to define the label anywhere you want. So you can refer to it first and then define it later. Now there is one restriction. Whatever is on the right-hand side of the equal symbol has to be an integer of some kind. Okay, so this one cannot be an open curly brace or something that's random. It has to evaluate to a particular value.
Multiple definitions of it. So
it cannot handle multiple
3
definitions.
equals 3 and then 3 equals 5.
Then the assembler will say, this is already, you're redefining a label, and that is considered an error if I remember correctly. You can always try out and see whether it's a warning or an error, but I think it is an error.
Oh, so it only works like the pound define. You can't just say 3 equals this value, and then later down the code, 3 now equals a different value because
It's not a variable.
we changed it.
Right, the definition of a label is one shot. Yep, you can only do it once. Now, on the other hand, you can use a label to define another label. Now, this is perfectly fine because with this definition here, this THREE is replaced with the value 3, this is replaced with the value 3, and then the value 3 plus the value 3 is 6, and that's why the new label, SIX, will have the definition of the value 6. Okay? Are there any questions at this point about labels? So labels come in handy, because it allows you to associate a symbolic name to a particular value. The next question is, what kind of value are we going to define labels to? That's the next question. It is also important to understand that label definitions don't take up any space in runtime. In other words, these are all convenience features for the assembler and for the person who's writing the program, so that you, instead of using literal constants, you can refer to the symbolic name. It also makes it possible so that you can change one definition of a label instead of having to search through your entire program to replace all the literal constants. I'm assuming that most of you already understand the importance of using symbolic name whenever possible, so that you don't use literal constants at all within your program. All right, and that part will be we'll re-emphasize that point over and over again. The current location has a symbol. It is a single period. Okay, that's the current location. In other words, as you write your program, depending on which section you're in, text or data, when you are writing your program or specifying code or constants and whatnot, you're constantly moving the dot along. Okay, so the dot is basically a bookmark that says, oh, this is the last part of that book that you have used. Are we doing okay so far? So every time you specify something, you're moving the dot, you're moving the current location down a little bit. If you want to skip some location, you can do that. You can actually use this particular method to skip several locations. In other words, you're basically saying, move the bookmark, by 20 spaces. So what happened to those 20 spaces that you just skipped? They basically become uninitialized. Okay? You're just saying, okay, I'm reserving 20 bytes, but don't do anything with those 20 bytes. So let's go ahead and talk about these two lines and try to find out what it does, okay? Or what they do together. The first one is saying, I'm defining a label called prompt, okay? And prompt is defined to be the current location. Once again, the current location can be in .text or in .data. It depends on which section is active at this point, okay? In other words, I'm just taking a snapshot. I'm just saying, look at the dot bookmark. I want to make prompt, point to the same place. Are we doing okay so far? Okay. So prompt doesn't change anymore after this definition. And then after that, I use the .ASCII's feature to define a string. And when we use this feature, or when we use this directive, it will use up bytes at runtime. In fact, in this case, it will use up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and then a null terminator at the end. So that makes 14 characters. Now, this is a useful feature because this allows me to use prompt as quote-unquote the address of the literal string. Okay. Now, I use double quote here. I said it is quote-unquote the address of, because prompt is technically speaking not an address. It is nothing more than a label. The label turned out to have an integer, and the integer turned out to be the address of the beginning of the entire string. Yep.
So do both those two lines go together?
Yes.
How do you know whether two lines are together or separate?
If they're adjacent, that means, well, okay, in this case, you don't want to put any more definitions between prompt equals dot and dot ASCII's, because otherwise, the prompt will just pick up the current location, right? So whatever is defined after prompt equals dot prompt will be the address of that thing.
Oh, okay. Now I got you.
Yep.
So is it in a single line?
Hmm?
Can you write that instead?
I do not think so, because I think the equal thing, has to be on its own line. And then on each line, you can only have one, directive, like .ASCII's or .int, .byte, they have to be on their own line. Yeah. So these two have to be on separate lines. Now, but because we want to do things like this, so often, there's a short form of doing it. The short form of doing it is simply to use, prompt colon, and then, whatever, you want to define. Now, yeah, the .ASCII doesn't have to be on the same line either, okay? Because you can just say prompt colon, which is the same as prompt equals dot. But in this particular case, the syntax does allow you to specify the label colon, which is the definition of a label, and also, something that will use up bytes, next to it. So it's a very handy feature. Okay, it's a handy feature. Yep.
So that'd be similar to like other labels where you go like _ start : you're just declared a label.
You're declaring a label to be the location of whatever construct that is following. Yep. All right, so I think at this point we can start to have some fun with the program. And so we got labels, we got the current section location, so all of that stuff is already covered. The next one has to do with i386 specific addressing modes. So we'll get to that at some point, but we want to go into the debugger and we'll write some really dumb programs that do not actually do anything. Okay. We like those programs, don't we? In fact, I can make a few homework assignments out of those, kind of dumb, sample programs that everyone is going to hate. All right, so we'll go ahead and write a very simple program. I'll just call this, memory allocation. That's too confusing to people who know what is malloc. How many people know actually what is malloc? Very few, because most of you use new with C++ instead of malloc in C. Yep. So we'll just say, okay, allocation 1, okay, because I might write several programs like this. All right, so we'll just go ahead and switch to everything is in the .text section, and then we'll say, you know what? I'm going to start with the definition here. I'll say .int. We'll give it something like feed dad. Hexadecimal is handy sometimes, because I can spell out certain words. Dinner time, I'm hungry. All right. But you will see that this one is actually kind of tricky when we examine the memory location. This is going to be fun. This is going to be one fun exercise. I'll define the label here. I just call it L1 because it doesn't really have any specific meaning to it. And then we'll have some dot word here. Okay, so we can say, okay, let's just ABCD. First byte is ABCD, and then we have just 5. Okay, and then we'll throw in something like ASCII's. quote tag. Okay. That's the entire program. Okay. In other words, this one does not contain any instructions. It only contains, well, I'm going to specify the instruction to exit the code, so that we can actually get to a breakpoint, so that we can examine those locations. But it doesn't really contain anything that's useful as far as instructions are concerned. But we'll take a look at how these memory locations are allocated. Yep, go ahead.
Is there a difference between quotes and double quote?
I do not think you can use double quotes. Well, let's find out. Did I use double quotes in my example?
No, not that one.
Okay. So then we can start, the program. We'll just, move L $1 to EAX, move L $0 to EBX, and then we'll do an int 0x80, which is the exit code. You will see these three instructions at the end of all the programs that I write. All right, so this is the entire program. So what can we possibly do with this program that is even slightly interesting? Well, I don't know about interesting, but I can do something extremely confusing with this program. Extremely. As in, 3 weeks later, there will still be people asking me, how did that work?
Little Indian.
Yes.
Little Indian?
Little Endian. Endian. E-N-D. Yeah, there are all kinds of jokes with that, but it's not politically correct anymore. Okay, so G steps, which includes the symbol table, which is very important because without that, it's kind of hard to make any sense out of the program. Okay. Junk at the end of line, first unrecognized character is 8. Okay, let's fix that. Line 6. Okay, I guess it is double quote.
So
There we go.
single quotes are not allowed.
Single quotes are the ones not allowed. It's double quote. It's one or the other. It's one or the other. Okay, so this program is now assembled. Let's do the linking. Oh, okay, I forgot to do one thing. Why do you think it's complaining? Underscore start is right here. Well, all the symbols that you define inside one file, they stay local to that file. In other words, if I just do it like this, underscore start is considered quote unquote a label that is local to this particular source file, which also means the linker, the assembler does not make it external, does not make it available to the linker. So when the linker says, okay, I'm supposed to make a, executable, and I need to know the label that marks the beginning of the entire program, it's not there anymore. Do you understand what I'm saying? So this is, for those of you who understand how to use the word static combined with global variables in C, everything is considered static. Okay, until you say underscore dot global underscore start. That's the same as exporting it. So what we need to do is to say dot global underscore start, which is basically telling the assembler and say underscore start is a symbol that may be useful by somebody else. So make it available to the linker so the linker can now see this particular label. So this is what I missed earlier, and that's why the linker did not work. And now, okay, why is it still not working?
You have to recompile it.
Because I did not reassemble. Very good. Okay, so I have to reassemble.